Hello everyone, this is Dr. Webb. We've already talked about how to find derivatives at a point, thinking about derivatives as representing the slope of the function at the point, or the derivative being the slope of the tangent line at the point, or, the derivative being the instantaneous rate of change of some real life function at a particular value. But now we're going to look at the derivative coming out of this as being a function in and of itself. So here's the idea of derivative that we've been using so far. We've been trying to find it at some particular point A. Originally, we thought about it coming out of this limit of secant slopes. Where, f of x minus f of a, that's talking about the change in the y values. The x minus a, that's talking about the change in the x values. And when you have a change in the y values divided by the change in the x values, that's a slope. It's a secant slope because it's talking about two different points on the function. And then it becomes the tangent slope by taking the limit, by moving the 2 points closer together. We've also talked about it in the last video as a limit of average rates of change. So this delta f over delta x, this is thinking about it more as an average rate of change. And in all of these, we've been focusing on trying to find this for some particular x value, which we've been calling x equals a, right? But we can do this for a whole range of x values at the same time, and there's nothing particular about a, though. And so we're going to do a little change of variable. In particular, we're going to be talking about f prime of x, and so we want to change a into x. So x is going to be now the value that we're evaluating this at. And so where we have x before, well, we're already going to be using x in the role of a, so we got to call it something else. And so we're going to, instead of thinking about x, we're going to think about it as being x plus delta x. So think about this as being, we've moved a little bit over from x. We're moving a little bit over, either positive direction or negative direction. And then in the limit, the x going to a, well, this would become x plus delta x going to x. And so if x plus delta x is going to x, well, really, you can think about canceling off the x's on both sides here. What we're really saying is that the delta x, the change in x, is going to 0. And so in our limit, we're going to be replacing x goes to a with delta x goes to 0. So with this change of variables, this new formulation of this is we get f prime of x is now going to be equal to the limit as delta x goes to 0 of f of x plus delta x. So that's x shifted a little bit over and then plugged into the function minus f of x. And then on the bottom, it's going to be just delta x. And the thing to keep in mind is that this delta x, what this really is coming from, is that it's x plus delta x minus x, but then these x's cancel themselves off. And so we're left with just delta x. And so that's why we have just delta x in the denominator. And the key thing about this is that now we have rewritten this as a function of x, similar to f of x at the beginning. So this is now a function in and of itself. And how do we get the values of this function? Well, we do this limiting process all over the place. Now, often, to make things a little bit shorter, rather than writing delta x everywhere, instead of delta x, and this is often used in books, the letter h is used. And so if we swap that, this limit definition becomes this. So now it's the limit as h goes to 0, f of x plus h minus f of x divided by h. And so again, this delta x and h These are playing the exact same roles. Okay, so here's the limit definition that we have so far. So again, this is still representing everything that we saw before. This is still talking about, we are still taking a limit of secant slopes. We are still taking a limit of average rates of change as the distance between the points go to zero. It's just now we're either using delta x or h to represent that distance between the x values. So some other notation that's often used instead of f prime of x is, we could say d over dx of f of x. And so in this situation, this d over dx, often this is, well, technically the name would be, it's an operator, and it's saying take f of x and stick it into this limit that we see above. And so this d of dx of f of x is kind of saying take the derivative of f of x. Some other shorthand coming from that is df dx and dy dx. And really for all three of these, this is really tying into that df dx, or any one of these, is really coming from taking the limit as delta x goes to 0 of delta f over delta x. And so this d here is really coming from, it's a change of from delta, which starts with d, into just d. Okay, and so delta x we're thinking about as being delta f and delta x. These are actually representing real values. Delta x is not actually ever equal to 0. It's just going toward 0. And the d over dx, you can kind of think of, that's what happens when delta x becomes 0. One other bit of notation, d of f, sometimes you see this, it's not so much, it's not something that I'm going to be using very often. But in some places, when they say take the derivative of f, there'll be a capital D of f. So anywhere where we can take this limit, so where f prime of x exists, we're going to say that f of x is differentiable then there. Right? So for most of the functions that we're going to play around with, pretty much anywhere that f of x exists, f prime of x is going to exist as well. So we'll say that those functions are differentiable everywhere. So it turns out that if you're differentiable, then you have to be continuous at that point as well. And that's really coming from looking at this limit definition. So being continuous, this is the same thing as saying that f of x plus delta x goes to f of x as delta x goes to 0. Well, not only does f of x plus delta x go to f of x, that has to happen in the definition of derivative, because as delta x goes to 0, this numerator has to go to 0 as well to kind of cancel off the 0, the delta x going to 0 in the bottom. If this was going to some other, if this was not going to 0, if this was going to any other value or not going to anything at all, there's no possible way for this limit to exist, right? So continuity here, this is absolutely necessary for the limit to exist. And if it's differentiable, that means that the limit exists, so f of x has to be continuous. So the key thing is, for the limit above to exist, f of x has to be continuous because we need f of x plus delta x to be going to f of x, so that f of x plus delta x minus f of x goes to 0 as delta x goes to 0. So to cancel off that 0 in the denominator. Okay, so let's let f of x and g of x be differentiable functions. So these are functions where the derivative exists, and we're going to let c be a constant. Well, what happens if we take the derivative of c times f of x? So let's plug this into the limit formula. Let's use delta x going to 0 of, well, if I plug in x plus delta x, so this would be c times x plus delta x minus c times f of x all over delta x. Well, this c inside the limit, we can just pull this out. And so we can have c pulled out of everything up top and completely out of the limit. All over delta x. And so now this is just the constant, and we have back, this is f prime of x. So taking the derivative of c times f of x is just going to give us back c times the derivative of f. And so that's what it is. So anytime that you have a constant being multiplied to your function inside the derivative, you can just pull that constant out. So pull out. What if we're adding f and g together and then taking the derivative? So actually, let's use h for this one. Let's get used to that. H goes to 0. And so plugging in x plus h here would give me f of x plus h plus g of x plus h minus f of x plus g of x. And this would all be over h. And so again, remember, h here is x plus h minus x. And so that h on the bottom is still, we're still thinking about that as dividing by a distance in the x direction. Okay. And so then we can rearrange the top here if we distribute the minus to be f of x plus h minus f of x plus g of x plus h minus g of x, all divided by h. And so then at this point we can actually break this up into two separate limits. Minus f of x all over h. And so this is using limit rules that we saw before. And now this first limit here, this is the definition of f prime of x. This second limit here, that is the definition of g prime of x. And so we end up with f prime of x plus g prime of x. And so the derivative of a sum is equal to the sum of the derivatives. So let's write that out. Derivative of a sum equals the sum of the derivatives. Okay, so let's work out some derivatives of some common simple functions. I think we might have done some of these before, but let's just hammer them out. These won't take so long. So what if we're doing the derivative of just x? So limit as delta x goes to 0, plugging in x plus delta x, I'd have x plus delta x minus plugging in x would just give me x. And this is all over delta x. And so looking in the numerator here, the plus x on the left is going to cancel off with the minus x on the right. And so we end up with taking the limit of delta x over delta x, and they're going to cancel off to 1. And so we're just taking the limit of 1. And so our derivative is 1. So the derivative of just x by itself is always equal to 1. And so then using sort of the rules that we saw before, if I wanted to take the derivative of 5x, well, this would be equal to 5 times the derivative of x, because I can pull the 5 out. And then the derivative of x we just saw is 1, so it's going to equal 5 times 1, which is 5. What if we're taking the derivative of just a constant? Well, if I plug in x plus delta x into the constant, it's still going to be c minus c up on top, all over delta x. And so really, I'm taking the limit of 0. And the limit of 0 is just 0. And so anytime that we're taking the derivative of any constant, it's always going to be equal to 0. Finally, let's take the derivative of x squared. So this one is a little bit more exciting. Let's use the h goes to 0 here. So if I'm plugging in x plus h into there, then that gets squared. Minus x squared all over h. And I think we did something like x squared before. We were using the other definition. And so the algebra actually works out a little bit different using this definition, but it ends up being the same thing. So if I expand out x plus h squared, I get x squared plus 2xh plus h squared minus x squared on top all over h. And the 2x squareds cancel themselves off. And then I can pull out an h on the top, have 2x plus h times h. 2x plus h times h would give me 2xh plus h squared. And then dividing by h. So those h's get canceled. And now left with 2x plus h. H is going to 0. Nothing's changing the 2x. And so we're left with 2x as our answer. So the derivative of x squared is just 2x. If we wanted to take the derivative of 1 over x, let's use delta x this time. So this would be 1 over x plus delta x minus 1 over x all over delta x. Now I've got fractions in the numerator, and so to get rid of all the fractions in the numerator, I'm going to multiply by x plus delta x to get rid of the fraction on the left, and then also by x again to get rid of the fraction on the right. And then I have to multiply it to the bottom as well. So at the end, I'm only multiplying by 1 and not changing the limit. And so when I multiply this through, when I do x plus delta x times x and then divide by x plus delta x, that's going to cancel off the x plus delta x's. So that's going to leave me with an x there. Minus when I multiply 1 over x to x plus delta x times x, the x's cancel. And so I'm going to be left with the x plus delta x. And then I have delta x on the bottom, x plus delta x times x. And now, if we distribute this minus sign, I'm going to get minus delta x there. And then the x minus x, those two cancel themselves off. And so I'm left with limit as delta x goes to 0 of delta x on top, and then delta x times x plus delta x times x on the bottom. And this should be a minus sign up on top. That's important. I don't want to forget that. The delta x's cancel. leaving me a minus 1 on top. And now I can take delta x going to 0. Now I can run through the limit because there's my only delta x. It's going to 0, and I'm going to be left with minus 1 over x squared. And that's my answer. That's my value of the derivative. So the derivative of 1 over x is minus 1 over x squared. Okay, so let's close this out with one example. So we've got a bunch of things added together, and then we're taking the derivative of it. Well, from the derivative rules we saw before, we can just break this up and take the derivative of each of these individually. Okay, and then each of these have constants in them, and so we can just pull those constants out. And so for the last one, I'd be pulling out a 1/2, so I can get rid of that 2 and pull a 1/2 out. Okay, and so then the derivative, I have 3 times the derivative of x squared. Well, we just saw that the derivative of x squared is 2x. And so this is d dx of x squared minus 4 times the derivative of x is 1. Plus, well, and then here I'm just taking the derivative of a constant, and the derivative of a constant is 0. And then lastly, I have minus 1/2 times minus 1 over x squared, because that's the derivative of 1 over x squared. And then let's clean this up. And so 3 times 2x gives me 6x minus 4, and then minus 1/2 times minus 1 over x squared is going to give me plus 1 over 2x squared. And there's our derivative. There's our final answer. And you can see that's just as normal of a function as what we started off with. That is all for this video. I will see you again soon.